Hey, good morning. This is the gas laws notes, the lecture notes for day 1 of our gas laws unit. We'll be working some problems today and going through a lot with gas laws. So today what we want to do is learn about the kinetic-molecular theory. We're going to do some temperature conversions and pressure conversions and talk about Dalton's law to explain the behavior of gases. So you've seen a hot air balloon. That's silly. I know you have. Have you had someone shake up a soda bottle and spray it all over you? Maybe you've baked a cake. I've definitely eaten a cake. All of these are examples of the way gases work. Okay, so something interesting that you guys have probably heard of before, but I'm not sure, so we'll talk about it. When a scuba diver goes scuba diving, and they're several hundred feet underwater, the high pressures cause the nitrogen from the tank air on their back, the scuba tank, to dissolve in their blood. If the diver rises too fast, that dissolved nitrogen forms bubbles in the blood and is extremely dangerous and very, very painful. This condition is called the bends. Helium, which is less inert, less dense, and doesn't dissolve in the blood, is mixed with oxygen in scuba tanks, and that's used for very deep descents, so that doesn't happen quite so often. There is a whole lot of free space in a gas. Gases can be expanded as much room as you give them. If you give them a small container, they'll expand to the size of that container. If you give them an entire football field, they'll expand to the size of the football field. If they're in a container, they will fill the container uniformly and completely. They will take up every ounce of space. Gases will diffuse and they will mix very rapidly. The kinetic-molecular theory has a few parts to it. First part is gases do not attract or repel one another. Okay, they are not attracted, they don't repel one another, they're just kind of there, they hang out. Gas particles are small and have virtually no volume. Gas particles are in constant random motion, kind of like what I feel like, I'm in constant random motion. But yeah, gas particles constantly in motion. And all gases have the same average kinetic energy at the same temperature. So no matter what the gas is, it will have the same amount of energy due to motion, kinetic energy, at a given temperature. So if they're at the same temperature, they'll have the same kinetic energy. So the behavior of kinetic or real gases versus what the kinetic-molecular theory says. Real molecules have volume. Okay, we know that. Real gas molecules do have volume. Now remember, that was the kinetic-molecular theory. This has to do with real gases, the way they actually behave. The kinetic-molecular theory does not account for the volume of the molecules themselves. The kinetic-molecular theory assumes there are no attractions between molecules. Real gas have intermolecular forces, which we talked about a few units ago, that those gas particles can be attracted to each other. The attractions slow down. These attractions slow down the molecule and they reduce the amount of collisions. Otherwise, the gas could not condense and become a liquid. It wouldn't be able to do that. They'd be too far apart. So, properties of gases. Gases have volume, temperature, and pressure. We can also describe gases in amounts, as in the moles. And you know that 1 mole of gas has a volume of 22.4 liters. So, we have talked about moles and we have talked about the amount of a substance. And as far as gases go, the volume is 22.4 liters in a mole. But all these other properties can be used to model the behavior of gases. You can predict the behavior of gases based on the following property: pressure, volume, and temperature. Okay, so we're going to review each one of these briefly. You know what they are, but let's just talk about them anyway. Some vocabulary. So pressure is the force, the official definition, the force per unit of area on a surface. Okay, this is caused by the collision of molecules, and the standard measurement for pressure, these are standard measurements, like standard temperature and pressure. Standard pressure is 1 atmosphere, which is approximately sea level. 1 atmosphere is also equal to 760 millimeters of mercury, or torr pressure. And that is also equal to 101.3 kilopascals. These are differing units, but they all are the same measurement, 1 atmosphere pressure. That's also about 34 feet of water, but we don't really use that one. We usually mostly use atmosphere, millimeters of mercury, and kilopascals. A barometer is an instrument used to measure pressure. The pressure of air measured with a barometer was developed by a man named Torricelli. That's where we get torr pressure, in 1643. So a barometer, an old school barometer, mercury is the liquid that's inside the tube. Mercury rises in the tube until the force of mercury pushing down balances the force pushing up. Kind of like when you were little and you played with your straw in your drink. It's like how you can change the pressure. You can have a certain amount of liquid in the straw that you're using. This is kind of the same way that this barometer works. The pressure of mercury pushing down is related to the density of mercury in a certain height of column. Volume is the amount of area involved, so that's how much space something takes up. The standard volume is 22.4 liters per mole for any gas, and it can be any gas, not just the gases that are listed there. Also, a point to make note of, there will also be the same number of particles in a mole of gas. Okay, it's Avogadro's number of particles in a mole of gas, regardless of the type of gas. Okay. Temperature is a measure of the motion of gas particles. Bet you didn't know that one. It's a measure of kinetic energy. So standard temperature is 273 Kelvin or 0 Celsius. We will use mostly Kelvin in chemistry. I believe there may be something we use Celsius in, but it may not come till a little bit later. So most of the temperature measurements we'll use are in Kelvin. 273 Kelvin is standard temperature. This is just a picture of 3 different temperature scales, kind of giving you an idea. So 373 Kelvin, okay? It sounds like it's really hot. Well, it kind of is. It's 100 degrees Celsius and 212 degrees Fahrenheit, which is the boiling point of water. Pretty high. So down here we have standard temperature, 0 degrees C, 273 Kelvin. Just kind of give you an idea of what temperatures look like in differing scales. So talking about STP, I got to remind you what STP is. So it's not, don't panic. STP just means standard temperature and pressure. That's all that means. You'll see it a lot. STP used to be gas additive, by the way. That's where these old school advertisements come from. But STP now in our class is going to mean standard temperature and pressure. The standard temperature will be 273 Kelvin. Standard pressure will be 1 atmosphere of pressure. STP allows us to compare amounts of gases between different pressures and temperatures. Diffusion, another vocabulary word, is the spreading of gas particles through constant motion. Like how you can smell something far away. Like if a skunk sprays, you can smell it a long ways away. That's because these gas particles are in constant motion and they travel pretty far. They spread out as far as they possibly can, so you can smell that skunk way before you see that skunk. Compression is the pushing together of gas particles. Gases are the only state of matter that can be compressed. You can compress like an hour's worth of breathing air, however long, or an hour's worth of air that you breathe into a container. You can compress it into a small enough area that you can put it into a container on your back and go scuba diving. So that gas is compressed for you to be able to breathe. So it just means the pushing together of gas particles. All right, so temperature conversions. We're going to do some temperature conversions, and I promise you this is easy. Celsius and Kelvin are the 2 scales that we use in science, but mostly we're going to be using Kelvin, so we need to be familiar with that. To convert from Celsius to Kelvin, all you're going to do is add 273. So whatever the temperature is in Celsius, add 273. So if you've got Kelvin and you want to convert to Celsius, you'll subtract 273. Not hard. Okay, so we have some temperature conversions that I'm going to do down here in the document camera. If I'm going to convert negative 167 degrees Celsius to Kelvin, so what do? Well, if I'm going Celsius to Kelvin, I add 273. So I go negative 167 plus, because I'm adding 273. So negative 167 plus 273 is what? 106. So that's 106 Kelvin. Now we don't say degrees Kelvin when we're using Kelvin. It's just Kelvin. All right? No degree symbol or sign. Convert 321 Kelvin to Celsius. So we're going the opposite way. We've got Kelvin and we're going to Celsius, so we're going to subtract 273. Oop, there goes my pencil. 321 minus 273 is our temperature in Celsius. 321 minus 273, 48 degrees Celsius. Now, when we're using Celsius, we can use degrees. Okay? Converting 25 Celsius to Kelvin. So if I'm going Celsius to Kelvin, adding 273, 25 plus 273, 298 Kelvin. And 70 degrees C is equal to what in Kelvin? So if I'm going the other way, I've got Celsius and I want, oh no, I'm going the same way. I've got Celsius, I want Kelvin. I'm going to add 273. So 70 plus 270. Golly, this pencil's not cooperating today. Sorry about that. 273. 70 plus 273 gives me 343 Kelvin. Okay, not hard. Easy one. There's all our answers. Okay, so pressure is defined as force over area. We can convert between units using dimensional analysis, which I know you love that. We use this equality here. 1 atmosphere is equal to 760 millimeters of mercury, is also equal to 101.3 kilopascals. So we can go back and forth converting pressures, and you're going to have to. Trust me, we're going to make sure you have to. What's up with all these different units? Well, millimeters of mercury, we still routinely use that in medicine, meteorology, and aviation. That's still used. Kilopascals is what's used throughout the world and has replaced something called the pounds per square inch, which ask your dad about. They know PSI. That's your tire pressure, actually. So we're going to convert 840 millimeters of mercury to atmospheres. There we go. So I'm going to put my conversions up here. 1 atmosphere equals 760 millimeters of mercury. There we go. 760 millimeters of mercury. And it also equals 101.3 kilopascals. Okay, so we're going to use these conversion factors. So I'm going to use dimensional analysis. I start by writing my given, which is 840 millimeters of mercury. Wow, I'm just going to get a different pencil. It keeps breaking. Let me see. Find one that's not going to break. Okay, we'll go old school pencil. 840 millimeters of mercury. And what do we do? Disco down the unit. Put millimeters of mercury here. I want atmospheres, so I put ATM for atmospheres in the numerator. I use my conversion factors. 760 is in front of millimeters of mercury. 1 is in front of atmospheres. These units cancel, and I've got atmospheres. 840 times 1 divided by 760 gives me 1.1 atmospheres. 1.10 atmospheres. Okay, convert a pressure of 2.5 atmospheres to kilopascals. 2.5 atmospheres is my given. Disco down the unit so you know what goes where. Otherwise, you're going to make a silly mistake. I want kilopascals, so I'm going to put that in my numerator. I go back up to my conversions up here. 1 atmosphere is 101.3 kilopascals. Oh, hang on. Got to turn off my heater. Hot. Okay. So atmospheres cancel. I'm left with kilopascals. 2.5 times 101.3 gives me 253.25. So I can only have 2 sig figs. So let's see what that would be. What do you think? Well, that's 2 sig figs. The 3 does not round the 5 up, so my final answer is going to be 250 kilopascals. I know you hate sig figs. It's okay. Convert a pressure of 1.55 atmospheres to millimeters of mercury. So my given 1.55 atmospheres. Disco down the unit. And I want millimeters of mercury. So I go back to my conversion factors up here. 1 atmosphere, 760 millimeters of mercury. Atmospheres cancel. Multiply 1.55 times 760. And 1178. So I can have 3 sig figs. So what are you going to round? What do you think we'll round that to? 1180. Why? There's 1, 2, 3 sig figs. The 8 rounds it up. So it doesn't round to 118, silly. It rounds up to 1180. And the unit, millimeters of mercury. Okay, we're going to convert this pressure, 173 kilopascals. Disco down the unit. And I want atmospheres. So I'm going to use my conversion factors. There is 1 atmosphere for every 101.3 kilopascals. Cancel kilopascals. Multiply 173 times 1. And then I'm going to divide by 101.3. 3 sig figs, so I'm going to go 1.71. Yep, 1.71 atmospheres. That wasn't so bad, was it? I don't think so. Okay, Dalton's law of partial pressures. So there's John Dalton, handsome guy. Okay, look at those sideburns. Wow. Okay, so Dalton's law of partial pressure says the only variable in Dalton's law of partial pressure is pressure, so it's kind of nice. Pressures have to be in the same unit. So we learned about different units. You know, we have different units with kilopascals, atmospheres. To use Dalton's law of partial pressures, all the pressures have to be in the same unit, which of course means we're going to make you convert. For Dalton's law of partial pressure, the total pressure is equal to the sum of the partial pressures. Totally easy. It sounds complex, but I can assure you this is simple. Okay, don't overcomplicate it. Here we have a vessel with 0.6 moles of hydrogen gas. Okay, 0.6 moles right there, hydrogen gas. Here we have a container with helium. There's 1.5 moles of helium. So if I put both of these gases into the same container, the partial pressures of 0.60 and 1.50 add together for a total pressure of 2.10 moles of gas. Seriously, it's that easy. You just add the partial pressures together. If the first 3 containers will all put into the 4th, we can find the pressure that's in the container by adding up the pressure in the first 3. So here's our first 3 containers. Okay, if I have 2 atmospheres in this container, 1 atmosphere in this container, and 3 atmospheres of pressure in this container, what would be in this final one? All you're doing is adding them together. Right, 6 atmospheres of pressure would be in this container when we put all of these into the same container. This is gas and air. 78% nitrogen. Okay, it has a partial pressure in the atmosphere of 593.4 millimeters of mercury. Oxygen, look, more nitrogen than oxygen. Oxygen in the air has a partial pressure of 159.2 millimeters of mercury. There's a little bit of argon, 7.1% or millimeters of mercury, and a little bit of carbon dioxide, 0.2 millimeters of mercury. To find out the total pressure in the atmosphere, you add up the partial pressures of each one of these, the nitrogen plus the oxygen plus the argon plus the CO2, and you get 760 millimeters of mercury. That's where we get that number, okay? Partial pressures of all the gases in our atmosphere. So this first problem, if the total pressure, we're going to go back down here to the document camera, if the total pressure is 0.99 atmospheres, okay, so I've got total pressure equals 0.99 atmospheres. the partial pressure of carbon dioxide is 0.05 atmospheres. And it says the partial pressure of hydrogen sulfide is 0.02 atmospheres. What's the partial pressure of the remaining air? Okay, so we've got a partial pressure of something that we don't know what it is. Okay, it says that the total pressure, well, I'll do it this way. The total pressure is equal to the sum of the pressures. So P1 plus P2 plus P3 plus et cetera, et cetera, et cetera. However many there are. I've got total pressure, 0.99 atmospheres. That is going to equal the sum of the other pressures. So 0.05 atmospheres plus 0.02 atmospheres plus the remaining. So how do you think we would do that? Well, pretty easy. I would add these two together and subtract from 0.99. So I was trying to, yep, you can get it all in there. So 0.05 plus 0.02 is, oh no, 0.05 plus 0.02, there we go, is 0.07 atmospheres of pressure. I know my total pressure is 0.99. Okay, if I'm trying to find that, I'm going to subtract 0.07. And I'll get that. So 0.99 minus 0.07. The pressure of that, whatever that is, 0.92 atmospheres. Is equal to the remaining air. Okay, partial pressures add up to total pressure. A metal tank contains 3 gases, oxygen, helium, nitrogen. If the partial pressure of the 3 gases in the tank are 35 atmospheres of oxygen, 5 atmospheres of nitrogen, 25 atmospheres of helium, what's the total pressure? Okay, so I'm looking for total pressure. This time I'm looking for PT. I have pressure number 1 is 35 atmospheres. Pressure number 2 is 5 atmospheres. Pressure number 3 is 25 atmospheres. So total pressure is going to equal 35 plus 5 plus 25. So my total pressure is equal to 35 plus 5 plus 25. 65 atmospheres. Okay, kids, don't complicate it. It is truly that easy. All right, next problem. Scuba tank has a trimix of helium, oxygen, nitrogen. What's the pressure of helium? Okay, so we're looking for the helium part. If 0.39 atmospheres of oxygen and, oh, looky there, 78.58 kilopascals of nitrogen, total pressure is 1.5 atmospheres. So what do you think we need to do? Well, I told you they all have to be in the same unit, so I need to convert kilopascals into atmospheres, which we can do that. Okay, first thing you need to do, convert kilopascals into atmospheres. You're going to use that conversion factor. 1 atmosphere is equal to 101.3 kilopascals, and I get 0.7757 atmospheres of nitrogen. I can sub that in now. Okay, I now have my atmosphere's total pressure. Okay, I have the pressure of the oxygen, pressure of the nitrogen. Now I can find the helium pretty easily, right? So you can do 1.5 minus 0.39 minus 0.7757. There's a couple ways to skin this cat. So 0.3343, let's see if we did it right. Oh, they did it the other way, but that's okay. We end up with 0.3343. You combine like terms, you can do that also. Add 0.39 to 0.7757, and then you subtract from 1.5. You're going to get 0.3343. Okay, I told you we'd make you do that. All right, a container contains a mixture of helium and argon gas. says that it contains 0.4 atmospheres of helium, and the total pressure of the combined gases is 2 atmospheres. What's the partial pressure of the argon gas? Okay, easy. So my total pressure, I went back to my mechanical pencil. I like it better. This one's too small. It's just too small. I don't like it. So my total pressure, it says, is 2 atmospheres. I've got some helium, so my pressure of helium is 0.4 atmospheres. And I'm looking for the pressure of argon. So 2.00 atmospheres is my total. 0.40 atmospheres plus the pressure of argon, whatever that is. Okay, I'm going to subtract 0.40 from both sides. I know what it is. You never know. You don't want to make a mistake. Okay, 1.60 atmospheres is the pressure of argon. Ooh, argon, AR. Okay, last problem. Here we have a mixture of helium, neon, and argon gases has a total pressure of 790 millimeters of mercury. Whoa, if there's 15% argon, 60% helium, and 25% neon, what's the partial pressure of each gas? Well, I kind of worked this out a little bit for you here. So 15% is argon. Okay, so 15%, it gives me the total pressure right here. Oh, see, that's why I quit using that one. 790 millimeters of mercury. So 15% of 790 is 0.15 times 790, which gives me this pressure. 60% is helium. 0.60 is 60%. 0.60% of 790 gives me 474. And then same thing, 25% of that 790 is neon, so 0.25 times 790 gives me this. So the total pressure is 790 millimeters of mercury. When you add them up, you can check yourself and make sure. Okay, you may want to look at that one again, but it's really not that hard. It's not that bad. You can do it. Okay, total pressure is equal to the pressure of the gases, and we're given total pressure. 0.15, 15% is argon, so you take 15% of 790, 60% of 790 for helium, and 25% of 790 is my neon. I add those together, that equals what I knew I had. Okay? I know it seems hard. That one's a little more tricky, so you may want to look at it again, but you're pretty smart, so I'm pretty sure you can get this one. Okay, so good luck. Do your homework, and we'll start on Boyle's Law, Charles Law, and Gay-Lussac's Law next time I see you.